Hi, I'm Barry Seavey, and this is my presentation for my Winter 2018 final project in Predict 454 Advanced Algorithms for the Northwestern Program of Master's Science of Predictive Analytics. The project that I undertook was the facial key point detection from Kaggle. The objective here is to predict facial key points on facial images. It has some applications shown here is tracking faces and images in video, analyzing facial expressions to get emotional sentiment. It has some medical applications for if a person's muscles aren't working the way that they're supposed to be. It could be an indication of a medical problem, as well as biometrics, face recognition. Say if people with their iPhone use that as their login sort of thing. This is all taken directly from the Kaggle website. So that's the basis of this whole competition. The data for it. We have 7,049 training images. That's with the key points given to us. There's 1,783 test images that we're supposed to predict. There are 15 key points that we're supposed to be able to predict for each. The test metric is the root mean squared error. There's the formula for it over here, so you can see y hat is the predicted level, the y sub I is the actual. The difference is taken squared, sum it all, average it out over all those, all the entries, and then you take the square root of it. One thing that this metric does is it tends to penalize very poorly made predictions. So if you're off by a lot, your penalty is a lot. Additionally, of note, this is a regression problem, not a classification. Since we're predicting a location, you have to throw out an XY coordinate of things, so it's really a regression problem, not a typical classification, which you find many image competitions being. More so with the data, we were given 31 columns. 30 of them are these location IDs, X and Y coordinates, and one image array. Here's a snippet from the data frame of the data given here for our training set. Lots of X and Y's with the given locations, mouth center, mouth corners, and all that. The very last column here, that's the data for the image that we had to take this and process it through to create the actual picture. The pictures are grayscale. So what we did was we took every single one of those things and divided by 255. So we scaled the images here, these values here, from 0 to 1. When we're going to use this in neural nets, that's what it needs. When we're plotting these things out and show them on the screen, we reshaped everything to 96 by 96 because that's the scale that all of the given location info is. So those locations for when put into the model were scaled from -1 to 1 by using this formula, subtracting 48, which is half of 96, divided by 48 for each of them. Doing some brief data exploration. Here's a list of all the key points that we want to find. Eye centers, corners, eyebrow locations, nose, and various points on the mouth. If you note these right here, the nose tip for the X and Y coordinate, those are the only values that have all 7,049 entries populated in the database. Everything else here has something missing somewhere along the line. Here's an example of one of the images right here. This is a pretty good one right here. You see a nice front head-on perspective of a person, and the red dots here are the identified key point locations, nose center, mouth corners, eyes, eyebrows, etc. Here's another randomly picked out one. However, this has only 4 key points indicated, so this is one of those ones that's missing a lot of data right here. This is a real common thing that you'll be seeing throughout here. Also, just kind of a note here, this is supposed to be the nose tip right here, and look how far down it is. And the bottom lip, it's pretty close to where it should be, but it probably should be down a little bit further. Eye centers aren't the greatest here either, so quality of data is certainly an issue with this data set. This here is just a bar chart summarizing what we just saw there. The majority of the data has 30 entries, X and Y coordinates, so this goes with the 15 key points. And the majority of the data right here has 8 values with that X, Y corresponding to that one image, like with the 4 key points, the 2 eyes, nose, and the mouth. What is apparent here is that we were given 2 separately created data sets with all this info here and just merge into one saying, here's your training data. So just from general perusing, the 15 key point data, which is what I'm going to refer to it here, is this group over here. We don't have as much of it, it's a lower quantity, but in general, it's a higher quality. The image looks better, it's more consistently taken in terms of zoom and centering. And the 4 key point data, much larger quantity, however, the quality of it is much more suspect across the board, so that's something they have to deal with here. This is the scatter plots of some of the training data locations that were given. This is focusing on the 4 key point groups right here. You can see the left and right eyes here, definitely centralized, or the majority of them are in a typical location, but some of them are strewn all about in various spots right here. There's some, way down low here, way off to the side. Look at some of the images that those coordinate to. This guy right here, it's off center. You can see the location right here. That's this dot right here. So, I mean, it's a legit picture. That's exactly where his eye is, but again, it's just one of those images where really probably should be centered and I should be looking around there, but have to deal with what we have. And there's another example of a real poor data here. This is a picture of a bulletin board with other pictures on it, and this is some of this data probably right here. So obviously a very poor piece of info given here, right here. This is the nose distribution, again focused in a general area, but some are kind of strewn about here, and even some really, really low. So look at some of these right here. The images isn't centered, and it even completely clips off the people's mouths. So this would be one of those things with some of the missing data. There's no mouth information here. There's no way you can even possibly guess as to what the mouth location is or looks like, because it doesn't exist in these pictures. Here's with all the 4 key points put together in one plot. It does look like some sort of abstract art, but the intent here is just to get a general idea of the spatial relationship between everything. Are the left eyes opposite of the right eyes? Is the nose above the mouth? Is everything kind of generally where it's supposed to be? And it looks like, for the most part, it is. Now, if we go to the 15 key point groups, here's the left eye, center, inner, and outer corner. The general relationship looks pretty much how it should be. There's some data that's like, say, way over here. Pulled out that image, and obviously there's some info here, or the info is present here, but it's located improperly, so that's why this one looks off and odd. There's another one here where it's a profile picture, not looking straight on. So some of the info, the eyebrows here are kind of guessing or something like that, and that's why you would see the left eye being way off to the side over here, different from what most of the others are. Here's the eyebrow, the inner and outer, generally spatially located properly. Some are off out in space here. Again, this image right here shows them somewhere over here. Here's another one, semi-profile picture, where they're kind of hanging out over here, a little further over than you probably would think, but again, more suspect data that we're dealing with. Here's the right eye with everything there in relation to each other. From a 10,000 foot view, it looks okay. Here's the mouth and nose. Again, everything looks relatively okay here in terms of their general relationship with each other. Some general intuitions they get from just examining the data. The 15 key point data is generally of a higher quality for the reasons I mentioned and have shown. The 4-1 is of a lower quality due to the varying zoom and the consistent thing of the nose and lip data just flat out being off and properly put in, as well as in general, direct and centered images are better. Say direct meaning like a straight on headshot, think of like a mug shot, looking straight on. And images centered, where the nose is roughly in the center of the grid right there. Those are generally better, see all the data, rather than something like a profile, a side view, or edge bias, like pictures pushed off to the side. Note that this is pretty much about all the feature engineering that one could really do with a lot of this. There's not when you're dealing with images, that's kind of a unique thing, although later on we'll get to something more where I'm going to change some of the data. Let's get into the modeling. First, I used Python using the Jupyter Notebook. I used TensorFlow and Keras wrapper. Many methods are possible to do here. Remember, this is a regression problem, so basically any regression algorithm can work. Even though we're dealing with pictures in that, it's still a bunch of numbers, whether it's in a funky matrix or in columns or whatever, it's still numbers, and it's a regression problem. but I'm going to focus on convolutional neural nets. I haven't ever done this before, nor have I used TensorFlow or Keras before, so the reason taking on this project partially is to get myself familiar with these methods here. For these initial models here, I started going a little bit simple. So with all those missing values right there, I took the data set and I just dropped all null values from it. So we went from about 7,000 something records down to 2140 for our initial modeling, just to get it kind of a baseline and see how we were doing, and then change from then. The first model, I just did a simple neural net. Again, this is the kind of canary in a coal mine here. I just wanted to prove out and make sure things work. I could load the data and run TensorFlow on my machine here. So started off this, you started to call it a sequential model, so it just kind of goes in an order. Then you start doing this model.add, just part of Keras. So you're adding these different things to the overall model one by one. Add an initial dense layer, 100 nodes. You have to tail at the input dimension of the images. This is 96 times 96. You throw an activation function, did rectified linear. And the last one here, this is the output, a dense layer of 30. Because we're outputting 30 predictions here, X and Y for 15 key points, so that's 30 right there. Our back propagation, stochastic gradient descent right here. Mean squared error is our measurement statistic, so that's going to be my loss. Fit the model on it, 100 epochs, so that it runs through the data 100 times. And this is the validation split, an 80-20 split of the data to check our error on for that 20% holdout. And here's what the results were, the calculation of the loss here. So, okay results, not the greatest, but like I said, it was the canary in the coal mine. I just wanted to see how it ran. Just for kicks, I took that model and I applied it to the test data. So here's the first 16 images from the test data. You'll be seeing this a couple more times here with the other models. So in general, look at those first couple of pictures. You know, the results actually aren't bad. You know, the center of the eyes were there. That's put it on the mouth, center point of the nose. It hit the eyebrows. For the most part, it was okay. This guy over here, the bottom of the lip might be a little bit too low. Center of the eye, so-so. This image right here, this is consistently has issues here. Her nose identification was way off. The top of her lip is somewhere in her teeth right here, so it's kind of blended away and you can't even see it. Eye center is off here. This guy down here with his bottom of lip is much lower. Bottom lip is a real tough one to predict. That's a common problem one. This guy, the nose is kind of slightly askew, but for a very simple model, the first run through, results not terrible. So then I went off to do a convolutional neural net. And here's the first one that I came up with. Sequential, and it just kept going on down here, and we'll get into this in a second here. One thing with convolutional nets, for the image files that you're passing to it, that's just my X data here, my X signification here, you have to pass on a 4-dimensional array, with the first dimension being the total number of images that you're passing on. Even though you say input shape, still 96, 96, 1, columns, rows, and color channel. You still have to do this last one here, so you do this -1 here into reshape, and it automatically counts that out. So documentation wasn't all that clear with it, but it's something that had to be done. So just so you know, if you're ever doing this, this could be a potential holdup. So back to the model. If we take a look at this first grouping here, this is a very typical of a convolutional net structure. Start with adding a convolutional layer, do an activation function. I'm doing ReLU on all of mine here, so rectify linear is just what I've been doing here. Then you do something like dropout, max pooling. The next one, convolutional layer, activation, dropout, max pooling. Next one, convolutional, activation, dropout, max pooling, and you keep going on down like that. Typically you go down in a reducing kind of manner here. And then at the bottom, throw everything together like a global averaging, and then our last output is the 30 dense layers right here, 30 node dense layer right here, the XY for the 15 key points. So and then here's where you run the model, tell it again, loss, mean squared error. You could save the weights and parameters of it as it runs through everything here. Save best only, so every time it minimizes the loss here, it'll save those parameters so you can load it up later, which is a really nice thing. I only ran this for 20 cycles through, and again the 80-20 splits for the validation. here is my results. So accuracy kind of leveled out after a short while, and the loss here tends to kind of converge a little bit. So it seemed like it was going okay. As I started to submit this to the site to kind of get a score on it, I was getting these terrible, terrible results. And I did things like I put dropout in there, I changed the batch normalization, I changed all sorts of things. I kept getting these ridiculously high numbers of root mean squared error of 63. And that, for the life of me, I couldn't figure it out for the longest time. However, eventually I figured out you need to rescale the results when you submit it back. Remember when he normalized everything, divided the images by 255, and then the XY divided by 48 minus 48, that thing? You have to reverse that process before you submit it. So I was submitting numbers like, zeros and ones to it when it was looking for numbers, 30s and 40s. So that's why my root mean squared error value was really awful. So don't do that. I took that model, then put that on the test images, and here's the first 16 again. And if we look at some of these problem areas that were before, remember the nose was really off. Well, it's still a little bit off, but it looks a little bit better. Eye center's okay. Bottom of his lip looks a little bit better. Down here, very much better. His nose, closer, not ideal, but and the rest of them, the values seem to be okay. So it looks like there's a little bit of an improvement here from the very simple model from before. So then I moved on to the second convolutional net. Here I made it a function here so it can grab it and run it easily a couple of times. One thing I did add here is this step here, with dropout equals false. So every time I ran this, when it ran it, it did not do a dropout at each of these levels right here. If I specifically told it that with dropout equals true, it would do it. So I wanted to test if dropout was going to help. Ran the model here for the first time, same parameters as before. I just ran it for more apex here, 300. And the thing, when I ran it, it took over 2 hours to run this model. So that's kind of like a typical run time here for a lot of this stuff for me. And here's what my loss function ended up coming out with. So I probably could have run it for less and would have gotten to some decent number here, but that's what it was. And I submitted this to the site, rescaling the data this time. And here are my scores, 3.2, 3.3 for root mean squared error. It kind of put me around in the 70s right there for amongst the 170 submissions. So certainly over halfway over the median there, around about 40th percentile, something like that. So not bad for the first run through. If you just take the mean predictions, I'm going to say the mean of every location, the center of the eye and all that, and you just submitted that, suppose you're going to get like a high 3s for root mean squared error or something like that. So these numbers here are better than that. Submitting that to, or applying that to the test data here, here's those same pictures again. I circled some of the areas where I saw some noted improvement. Look, her nose right there, much better. Eyes getting much more towards the center. I think his lip issue had an issue there. Look, square in his nose right there. The bottom of the chin's really good right there. So a definite noted improvement here over the last few. So this is definitely the best running model so far. I then ran that same model, exactly the same parameters and everything, but this time I said with dropout equals true. And here are my results right here. So got to the accuracy level pretty quick, and it kind of merged on the loss function right here kind of quick right there, but it kept going down right here. So I'm not sure, it's kind of jumpy and all that too. When I submitted to the site, these are the results. I got 3.5. So remember, I was getting like 3.2, 3.1 for the last one without the dropouts. So dropout's supposed to help with overfitting, but it didn't seem to improve my scores here. So in the future, I just said no more dropout for the models that I'm going to be running. I went into something called data augmentation. So neural nets and convolution nets, they like lots and lots of data. So remember, I'm only using less than 1/3 of the data here. So a couple options we could do. We could fix some of those null values somehow, or we can also do something called duplicate these images. Flip them, rotate them, translate them, and all that. These algorithms here, when it sees another picture, even if it's just a mirror image or something very similar to the other one, it's a unique thing. So it sees it as brand new data. So it's kind of a somewhat quick and dirty way of creating more data for yourself if you have sparse amounts. So the first thing I did was try to impute data. What I did was I took the entire data set, separate out the records that would be in that 4 key point category. So I had a data frame with just the 4 key points. I took those nose tips and mouth center bottoms, moved each of them by 5 units closer to where I thought they should be. Like I said, it was consistently they were off. I just kind of manually chose a typical distance that they were off, and I translated and I moved them. I then took this last model that we had, model 2, the without dropout, and applied that to the train data where it was only the null values, or only records that had null values. So I created a test set, a new test set from my original training data, but I separated out with only guys that had null values in it. I then took the results from that, the predictions from that, and imputed those values to replace the null values. So here's an example of when I changed those images, changed the location of the nose and the lip there. Here's an original one. When I moved it 5 units, nose is right on, bottom of the lip's right on, at least for this image right here. So I knew I was getting an improvement overall, the couple thousand images right here, so I figured that would help out my root mean squared error and be at least training for it in the end. So after all that process, did the imputation that ran it on the new test data, and here's what my scores were. 2.88, 2.5 for the public and private. So I jumped like 20 something spots in the hierarchy of everyone by just doing that. Here's again the model accuracy, the model loss right here to get a sense of what it all looks like. And here's our 16 friends again. If you look at all the problem ones, her nose okay, center of the eye out pretty good right here. This one not the greatest. Top of the lip okay, bottom lips there were pretty good. His nose square on. Center of the eyes are pretty good over here, so it looks pretty good so far, and per the numbers it is the best result I've gotten so far. Another data augmentation you can do is flipping. It creates a mirror image of each picture, but again the convolutional net algorithm sees it as all brand new data, like it's something completely new. Keras has this thing called image data generator where it can do that. You could also create flipped, rotated, translated, whitening, they call it, like, change the dithering and the contrast in the image and all that, so create this new data. It does it dynamically while the model's running, so it saves you memory, so you're not creating all new data in your files to submit, eating up all your memory. The one issue with it though, it only does the image. The key points aren't embedded in the image. It's a separate thing, separate columns in a data frame, and that thing doesn't do it. Looks like this data generator was meant for like classification picture problems, so that's a problem. Here's one that I manually did. If I took this image and flipped it along with all the data, you could see, okay, that would probably be a pretty good thing to have. However, the Keras image data generator only does the pictures and doesn't do anything with that, with the key points right there. So there's a way to go around this. You can create a new class that incorporates both the data generator flipping as well as the data frame swapping of everything. Some guy called Daniel Nuri, who I found online, he created this whole new class in this thing and this method of doing this. So I borrowed his code right here just to give it a test here. So my intent here is to kind of do a battle royale. My augmented data where I did the predictions, and taking the original data I used, that 22,000 something with the 15 key points to fully populated data, and I was going to do that and do the flipping to create more data. So I had a sparse amount. I want to create a larger amount of what I consider to be good data, compare it with my modeling imputation and see which one did better. Here's some of the code for that new class. There's the numbers that they did to flip the index locations and a bunch of stuff right there to do that. The fit nomenclature is a little bit different, but we're still using that same convolutional net that we used before and everything. The only thing I'm adding is this fit generator here, this image flipping. It took a little over 2 hours to run here, and when I submitted it, these were my scores. So slightly better than the regular convolutional net model that we ran, but still worse than the augmented data. So it worked, it helped, but my method of running the model and imputing the data worked better. So I don't know if it's just that there's more data in the augmented model version that I did, or if just that the stuff that I use has a lot more variability to it. Even though these are flipped images, it's, you know, things are in still the relative same location. We had stuff that was kind of all over the board, so maybe the added noise within the augmented data actually ended up being good for generalization and helping out with predicting. Again, here we are applying that model to everything. Similar results as to before. Again, the nose here was kind of an issue. Eye centers, same problems we had before, still the same problems. The good results are still the good results. So not a lot new happening here. The last thing I tried was an ensemble model. So while some of the models work well in some areas, they kind of lacks in others, like that lower lip is a consistent problem. So create separate models for each group rather than a single one for all. In theory, this allows the models, those smaller models, to focus on smaller areas and be more specialized on each of those features, so enhanced prediction. So here's a general ensemble method that I have. Create groups via the dict function, the dictionary function, so the model is going to cycle through each of those here. I'll give an example in a moment. I can use the same CNN model, however, got to add some code because the output structure is going to be a little bit different. I'll show that in a second here. Here's a couple of those dictionaries. So like the left and right eye centers, that's in one group. The model is going to cycle over these, make its prediction. Then it's going to jump down to the next one, nose tip, cycle through these here, make the prediction, and so on and so forth. Because that bottom lip I always found to be kind of an issue, that's a separate group unto itself. And the others keep going on down. I didn't show everything here. Here's the general verbiage for the ensemble, this method here. This right here actually is the cycling process for setting an ensemble group. So setting is that list of, or ensemble groups is that dictionary that we just showed right there. So first is going to go through this left and right center, then it's going to go through the nose tip and all that right here. So everything else pretty much is just the same, with the exception of this little group right here. We have this model layers pop that gets rid of the last layer that was in the model, so it kind of pops it off right here. That then being that dense 30 layer that's present in the simple CNN. The reason is that we're not predicting 30 points X and Y every single time. The first time through we're only doing 4, right? Center, left and right eye at the center. So X, Y of each, so that needs to be 4. Next items here, clearing out that data, and then the last one, adding a dense layer of length of size X, which is the length of the columns here, which is the length of the number of items in the dictionary that we had there. And the rest, again, fitting the model and all that. I also did this for 100 epochs. I tried something called ZCA whitening via the image data generator. Again, changing the contrast in the pictures. So supposedly the convolutional nets can see things a little bit better and make separation, usually by edge detection. I was also using the augmented data that I created. So I set that and started running, and I waited, and I waited, and I waited. If you take a look here, the first epoch here, 1 out of 100, took 7,427 seconds to run. That's over 2 hours for a single one. That's supposed to cycle over this 100 times, and that's just for the eye centers. So 200 hours for that, something like, you know, it's over a week of continuous computation just for those right there, and it's going to continue on through for the balance of everything there. So like, you know what, I'm not doing this. So I stopped it and said we have to reevaluate. Ensemble method 2 went down to 50 epochs, and I got rid of the ZCA whitening portion right there just to see if that would change things. Again, use the augmented data, the 7,000 images that we now have. And when I ran it, 7 hours and 45 minutes to complete everything. So I went from over 2 hours per epoch to 90 seconds per, just by pretty much eliminating this step right here. So while this Keras thing is pretty nice, automatically creating and doing things with your data, with your images there, it's a time pit, and it just seems to take forever to do, at least on my CPU. So after running that model, submitting that, I got my best results by far, 2.16, 2.45, so it put me at 48th out of 175. So by far my best results, and I'm pretty happy and pretty satisfied with that. The best results in the leaderboard, I think, are like 1.4. I think are like some of the real top 10 scores like that. So I'm not terribly far off. So I'm going to range you some decent numbers right here. So I'm pretty happy with this. So in conclusion and summary, in general, more data is better results. We pretty much knew that though with convolutional neural nets. I still suspect that the variability in my data here, even with the the eyeballs being off in the corners and all that stuff, I wonder if that just really does help in the prediction right there, at least in the generalization of predicting. Helps me prevent overfitting, focusing on, is it only in the nose, only in the center, that kind of thing. If I had time, I'd like to try a couple other permutations of the modeling process here. Varying the layers and the layer structure, quantity and all that, varying activation functions. I just did rectified linear. There's a whole bunch of others that could be tried to see if that would change things. You can do things like change your learning rate and your back propagation estimators. There's all sorts of things I just didn't have time to get to. And if I had a chance to get some more beefy computing, maybe some of these data enhancements like ZCA whitening, doing some rotating and translating, creating more data right there via the image data generator in Keras, I suspect that still would help overall. But like I said, it just takes far too much time with what I have here. I would also like to investigate image grabbing. There's like things called YOLO, RCNN. You've probably seen it where it has like a little, it searches the entire picture and then has an image box and it grabs something that it's looking for. So if it's training it to focus on, just say a face, even with the pictures that are like, way off in the corner, maybe it will go up, grab that, recenter everything, and then do the calculations and run the algorithm on it. Or you can maybe even train it to do something like here, find an eye, find a nose, find a mouth, so it could help the initial step of the convolutional nets, help it kind of focus itself and start off at a better position. Here's a summary just of all my results here. The ensemble method, by far the best. Next was the augmented data, where I made the prediction and imputed the nulls right here. So those are obviously by the next best. And then the general models, just running the run general model and then having to flip data with it, though in this case didn't change a whole heck of a lot. And the dropout there, using that model of dropouts, performed the worst of all here. That concludes my presentation here. I hope you enjoyed it and learned something from it, and good luck to everyone here.